indicate the formal charges. I think that's very important to know where the charge is going or where it's not. So if you do omit formal charges here, there will be some deduction, let's say. I know former class members, when they would give me pens, because I would collect different pens, they would always test it off and write minus 0.5 formal charge, because I need a stamp that shows it, because that would be the key thing. So please include the formal charges. One last point with these general mechanisms is a lot of times you're going to see this species here, I'm highlighting H3O plus or hydronium ion. And I don't know if you ended up seeing this last semester in your class or not, but this is a generic acid, and I didn't say any sort of space for this before we get to the cyanohydrin. Because I can put it down here. I don't want to distract from the mechanism because that's so important. So if you see something like H3O plus, and you're wondering, well, where does that come from? It's like some random acid that came out of nowhere. This oftentimes is coming from, say, sulfuric acid and water. So since sulfuric acid is a much stronger acid than water will just pick up a proton from the sulfuric acid. Right? And so you'll end up with the conjugate base. This was a bad idea, writing it down here in the corner, plus H3O plus. And you just need pretty much a drop of sulfuric acid, because if you have water in your reaction, there's 55 molar water around compared to everything else. And so you just protonate a little bit of it. So whatever the amount of sulfuric acid that you added, it's pretty much just going to protonate the water. So then you have some hydronium around. You could use other acids. HCl is fine with hydrochloric acid, but then you just want to make sure the chloride is not going to do anything. But this sulfate is such a poor nucleophile because of all of the resonance induction effects from 220A. Make it all draw resonance structures. All these electrons are being taken away from the oxygen by induction. So that's why sulfuric acid is oftentimes used. And we're a little bit lazy in balancing things. So I know in Gen Chem, balancing equations is everything, where sometimes here you'll just see water or acid float in and out of the reaction because it's all around in the actual reaction. If it's say done in water or something like that in this particular case. So that's why it just acid appears, water appears over here, and so on. Okay, so now going back just finally, I strongly encourage you not to memorize, but to be very familiar with these two sorts of mechanisms, because I think this will really help organize a lot of the things that we talk about later on. So now let's consider a couple of reactions, and actually we've already discussed some of these. At least in the next step. So one of the common reactions with an aldehyde or a ketone is what's known as cyanohydrin formation, as it's indicated here. And if we take this particular aldehyde, benzaldehyde, as it is in the case, and a small amount of hydroxide, we're going to end up with a product that has an OH and a CN here. And this species is known as a cyanohydrin. I don't think that's even close to legible. Cyanohydrin. These are actually quite useful compounds because this cyano group or nitrile group can be converted to other functional groups, which we might end up seeing a little bit later on. We don't really need to worry too much about the details of the mechanism, but just overall, it follows what we've seen. Generally, because HCN is not a very good nucleophile, this was done in these slightly different conditions so that we have hydroxide plus a little bit of HCN. It's going to take this proton off to form water plus CN minus. Now it looks like we have a good nucleophile. So let's rewrite down here our aldehyde, our cyanide ion. So I would attack the carbonyl group. Electrons move up onto the oxygen. This one I'm going to write, I'll stick with the equilibrium arrows, so to be consistent. O minus, I'm going to pop the cyano group up in the top so it looks like it is in our product. And then all we need to do is to protonate. So we could have a little bit more water around. OH, and then the cyano group. So nothing really new in terms of the reaction mechanism. This is one of those reactions that it's really easy to write on paper because we can just have our strong nucleophile attack, form our tetrahedral intermediate, form our product. I'm not showing stereochemistry here, but this is a chirocarbon. But this is a reaction that most of the time we'd want to avoid doing because this is actually hydrogen cyanide. So this is not something that we want to use normally in the lab because of its toxicity, but it has a history of being used to make these cyanohydrin compounds. But I just want us to be aware of that. So it really just follows the same pattern. Now as we're going through this, the next thing I was going to have is this formation of a hydrate or a gem diol. But this is in actuality, this is what we already saw. We saw that under basic conditions, let's use rather than a aldehyde, let's just use a ketone, right, basic conditions. Take something like acetone with sodium hydroxide and water. Now we know that, oops, I wanted to use red. We're going to generate a tetrahedral intermediate, which I'm not showing the stereochemistry now, just in a more generic reaction. And our water will then end up protonating this. So this is the reaction. It was our generic reaction above. Just I'm showing it again now with a ketone. OH and OH. Those are supposed to connect to the same spot. Plus hydroxide. So I know this sounds like it's repetitive because it is. I didn't draw the formal charge here, but negative formal charge, negative formal charge, negative formal charge. So that checks out. And as mentioned above, this species, this is known as a hydrate or a gem diol. A diol means two alcohols. So it's a di-alcohol, diol. And then gem is short for geminol, which means that they're both attached to the same carbon. And then the hydrate is exactly like what it sounds like, is that we hydrated this compound. We added water to the compound. So we added OH, which could be this OH, let's say, and another hydrogen at this position. So this compound here is the hydrated form of this ketone. I'll scroll up for a second. Yes. Is that okay? So this is the hydrated form of the ketone, and you could dehydrate it by, say, going back to the actual ketone. Okay, excellent. Is it all right if I scroll down just a little bit? Yes, all right, thank you.